So this is example 6 on page 41. Every single question that we are dealing with yesterday or today involves horizontal projectile motion. And I realize that if you've ever played baseball, you don't always throw the ball horizontally. You do if you're trying to get there as quick as you can. If you're trying to get the ball to first base as quick as you can, you're going to fire that ball horizontally. You're probably going to fire it from a higher level because you know it's going to drop a little bit. But that's the first base person's job, to go up and down and catch it. Okay? If you're in outfield and you have a ball and you want to throw it into second base, you're probably not going to throw it horizontally. Because what's going to happen is it's going to hit the ground before it hits second base. You're going to throw it up at an angle. And we're going to be looking at those next week. So during the flight, the ball drops 1.8 meters. How fast was the ball thrown? We should understand that this question is saying, what is VI? And I really want to dig down deep today and talk about what it means when I say what is VI. When I say what is VI in projectile motion, and I don't make any reference to X or Y, I'm saying that's the initial velocity, period. Which in this case is so many meters per second horizontally. I'm not saying that's VI under the vertical column. So if I don't put an X or a Y here, if I don't put an X or a Y here, this is that velocity I'm talking about. Because when you look at the initial vertical velocity, it's 0. So when you add the initial vertical and the initial horizontal, you get the true initial velocity. I mean, if you like, I can call this X. But when I talk about VI, and this gets tricky, this velocity of the ball, which is what we're after, is this number here. But the velocity of the ball a short time later will no longer be this number. It's going to be the sum of this and whatever the velocity vertically is. Okay? If you like, if that bothers you, you can dispense with the I and simply say to yourself, well, we're trying to find the horizontal velocity because that's the velocity it was thrown at. But a little bit later, we're going to introduce a different type of question where you need to wrap your head around the fact that we have a horizontal velocity, which is always the same. We have a vertical velocity, which is always changing. And we have a total velocity, which will always be changing, which is the sum of the horizontal and vertical. Anyway, just to cut through all the red tape, this is negative 9.81. I'll leave the units out. The displacement of the ball is negative 1.8 meters. We want to find Vx. We know the displacement horizontally is 10.6 meters. But in order for you to find the answer to this question, we need to know the time. We don't have enough information in this column to find the time. Man, these projectile motion problems, if anything, so far, they're giving us a real workout becoming familiar with this equation, aren't they? Because, I mean, you almost always use it. Maybe always. So we can use this to find the time. I'm going to give everybody a minute or so to crunch the numbers to determine the time. We're going to take the distance and multiply by 2 and divide by the acceleration. Again, I'm not using negatives here because I know they're going to cancel. In addition, I'm not using negatives because I know I can always call down positive if I want to. Because there's no change in direction, you don't need to worry about vectors. And I take the square root of this answer, and I get a time of about 0.6 seconds. Anybody else? Okay, good. So you get we'll call it 606 doesn't matter what I call it on paper, I'm going to use all of the decimals that I can in my next calculation. So in my next calculation, what do we have? Distance equals speed times time. How many of you are starting to gain an appreciation for the fact that you can recognize when vectors are definitely not important? You know, like vectors are not important here in this calculation. If you want to include them and you want to say direction is towards first base for the velocity and the displacement, feel free. All I need to do is multiply these now. Where am I? There we go. I need to multiply that by, no, we know the distance. We're trying to find the speed, aren't we? Okay. The speed is the distance over the time. So we need to take that speed calculation to be 10.6 divided by our answer. And you get about 17.5 meters per second. So let me come back to my point about the whole VI, which is not necessary for you to understand this question, but I'm trying to, build up those mathematical and physical muscles for you, physics muscles for you for later. This number that we found is Vx. Okay, it is. It's the horizontal velocity of the ball, which is the horizontal velocity of the ball initially when it was thrown, which is the horizontal velocity of the ball at any point in time, but it is also the initial velocity of the ball at the beginning. It's not the velocity of the ball a short time later, because a short time later we will have that horizontal component and a downward vertical. And the hypotenuse of what I'm showing you would be the velocity. Any questions with 6? All right, number 7, a bullet is fired horizontally with a speed of 450 meters per second at a target that is 300 meters away. How much higher than the target should the shooter aim? If you've ever done any high-power rifle shooting at long-distance targets, you know that the scope is adjustable up and down. And you adjust the scope based on the distance that you determine. And there's something called a rangefinder. You can look through a rangefinder and read the distance. The idea is, even though the bullet is moving so fast, it falls over a long distance. It's a little trickier with bullets because there's a lot of friction and that affects things, but we're not going to get into that. So if the center of the target is here, and you take the bullet and you fire it in line with this, with a particular velocity, you are going to miss the target. Because the bullet will end up, the bullet will end up falling. And you may not think it's a significant distance, but 300 meters is a long distance. I do realize that at 450 meters per second, the time is still not that great. It's going to be less than a second to hit the target, to go that distance. Okay? But in that less than a second, things can fall quite quickly. Well, not quite quickly, wrong way to put it. In that short period of time that's less than a second, the bullet can fall significantly. Right? If you just take, and we'll get back to this question in a second, if you take this equation, d equals 1/2 at squared, and you say, well, how far does an object fall in half a second? You'd put a half here and 9.81 there. Do that, just for kicks. Just put a half second is a short period of time, right? You can't even say a word in half a second. .5 times 9.81 times 0.5 seconds squared. I'm just picking 0.5 because it's 1.2 meters. You getting the same number? That's staggering. You wouldn't think that an object falls that far in half a second. What that means is when I drop an object from here, it's going to hit the floor in half a second. Gravity is pretty significant. So what are we going to do here? We want to take this and move it up so the bullet hits the target. And what we want to find is, and this is not going to be to scale. There's no way I can draw this to scale because this distance is 300 meters, right? But what is going to happen, and I'm going to draw this and then I will adjust my diagram, is the bullet will do that. So this is a diagram showing what's going on. And it's a little too horizontal initially. It should have started going down right away, my green curve. But you get the drift. So we want to find out what this distance is. We know what this distance is. We know the acceleration due to gravity, which is a vertical acceleration. We know the horizontal velocity, which is going to be Vx all the way through the bullet's journey. So we can do our XY deal. And I would hope that these are getting to be you're very comfortable with these questions now. They're very basic. So VI in this column is 0. D in this column is what we would like to find. T we don't know, but we're going to need to know it to find D, I suspect. A is negative 9.81. And that's all we know about the vertical aspect of what's going on, about the Y components of what's going on. And as I've said before, but I will remind you, with kinematics equations, all those VI, VF, ADT things, you need 3 things to find a fourth. You cannot find anything if there's only 2. So we can go over here and say that V, I don't even want to put vector symbols here, is 450 meters per second. In fact, I really am not going to put vector symbols because if I do, then I'm forced to write direction in here. And I don't care about the direction. And the distance is 300 meters. So the time is the distance divided by the speed. It's at 0.67, I think, 0.666. Is my thinking correct there? Clear? 0.6 repeating seconds. I might as well write 0.6 repeating because I want to now put it into this list and use it in a further calculation. So think about this. I just picked half a second just to talk about the significance of gravitational acceleration on objects over even a short time of half a second. This is more time. So we can calculate the distance using 1/2 AT squared. And again, we've done this so many times, I feel as though I don't need to write down 1/2 times 9.81 times 0.6 repeating squared. And I'm not going to include the vectors. So we're graduating in this course to a point where we can cut some corners even though we technically should be including vectors. Who cares? If I do include the negative in the 9.81, then I will get D being negative, which means it's a negative displacement. The bullet drops. I will do that. 0.5 times negative 9.81 times 0.6 repeating. My calculator ought to get my drift here, squared. So we're getting 2.18. Okay. Now think about this for a second. There's a lot, we're vastly oversimplifying things. Okay. So you're in the target section of a triathlon in the Olympics, and you have to lay down on the ground and hit a target. Let's say the target was 300 meters away. You're not going to climb up on top of some boxes that are 2 meters above the ground, right? You're just going to aim higher so the bullet goes up and down. But if you fired the bullet horizontally, then you would have to be aiming over 2 meters higher than the target. That's pretty amazing. That's a significant distance. You know, yep.
Because of the way the question is worded, how much higher do you have to aim? Would the displacement be positive?
Yes, yeah, let's talk about that. So this is very similar to kinematics questions where you might be given information about an object thrown from the top of a tall building and it says how tall is the building? And when you calculate the displacement of the object, you get negative 40 meters, which means the answer to the question is the building is 40 meters tall. So you are absolutely right. This number is the displacement of the bullet. So I'm even going to write that down with a vector here. It's a good point, and I think I would have just walked over that and forgotten about it. This displacement of the bullet is negative 2.18 meters, which means what the question is asking, which is how much higher would you have to shoot? The answer is you would have to aim 2.18 meters higher. We wouldn't say negative 2.18. So the answer to this question is 2.18 meters above the target. Another interesting thing about this question and the concept of shooting a bullet is this is a very high-powered rifle. This speed of the bullet is greater than the speed of sound. What does that mean? It means if you were using it to hunt, the bullet would hit the animal before the animal heard the shot. There would be impact, and then you would hear the shot. Well, maybe the animal would hear the shot. Okay. All right, let's talk about B quickly here. I think we've kind of asked this question to death, haven't we? What are the two physics principles, and in which order did we use them? So what did we do? We used uniform motion first. We did a calculation here on the left-hand column, which is our uniform motion because it's using speed equals distance over time, followed by an accelerated motion calculation. So the answer to this question would be 0, which is the number corresponding on your formula sheet to uniform motion, followed by a 1.